It just says that energy comes from somewhere. Energy can't be created or destroyed. It has to have an origin, right? We define energy as the capacity to do work. It's kind of a weird definition. Work is the ability to exert a force on an object over a distance, expend energy, and so possessing energy is the capability of doing work. In a lot of problems, or in a lot of discussion about the first law, you're going to see the case that they've divided the universe into two components, a component called the system and a component called the surroundings. And if energy is conserved, if the total energy of the universe doesn't ever change, and if the universe is composed of these two subsystems, the system that we're concerned about, whatever our experimental system is, and everything outside of it, then we can state mathematically, we can make this mathematical statement of the first law, which is that any change in energy of the system has to result in a change in energy of the surroundings, and the sum of the changes has to be zero. That's just a restatement of the first law. Energy has to come from somewhere. If we've divided the whole universe into two places, then energy that comes from one place has to be expended in the other, right? And that's all this equation says. You'll see that equation frequently from this point forward. So total energy of the universe is constant. And if we're going to talk about energy, I want you guys to have a really strong idea of the different ways that energy can be stored in molecules. We're going to be going into some things, and we'll be looking at very specific ways that energy, some simplified and specific ways that energy flows in and out of certain systems. But we're not going to be dealing with all of the different possible ways that energy can be held in systems and transferred back and forth. We're just going to kind of step outside of the system and look at its bulk properties. But that said, I still, before we go into these calculations, I want you guys to have a very strong understanding of how energy is stored in molecular systems. So that leads us to the next page of notes, I believe. Or it's not the next page of notes. Okay, so we have kinetic energy. You guys know what kinetic energy is, right? You got a mass, it's traveling with some velocity, it has an energy, right? And molecules store kinetic energy. The way that we've been looking at the kinetic energy in molecules is through their translational motion. What we didn't talk about was that translational motion is not, translational motion of the molecule's center of mass, let's say, is not the only kind of, or the only mechanism that molecules have for storing kinetic energy. They can also have kinetic energy that's stored in molecular motions that don't result in translation of the center of mass, but that take place while the object is held still. Those motions are vibrational motion and rotation. So a molecule has bonds, right? And those bonds are kind of, you can think of them as a spring, right? They've got some force constant. You start to break, you pull them apart, and there's a restoring force. Well, those bonds can vibrate. And when you have bonds vibrating, the two masses at either end of that bond are moving, right? You have two masses moving back and forth. And so those masses have kinetic energy because they're in motion. And so vibrational motion is a mechanism for storing kinetic energy in molecules. Yeah? Similarly, rotational motion, if you have two masses, and say there's a bond between them, and they're rotating about that bond. Do I need to draw these for you, or do you get the image?
No.
I actually would like to see them.
Okay. So,
But there are 6 in total, right?
what's that?
There are 6 or 7 in total.
6 or 7 total what?
Modes. I mean,
Modes?
yeah.
Well, the specific number of degrees of freedom depends on the number of molecules involved, but right now we're just kind of speaking generically about rotational, vibrational, and translational motion. So rotational motion, you have two masses, right? There's some bond. If these masses are rotating, right, they're turning little circles about the center of that bond, then you have a mass in motion. Anytime you have a mass in motion, you've got kinetic energy, right? And so rotational motion of a molecule is a way to store kinetic energy. Take these two atoms and you allow them to vibrate and move back and forth. Now you've got mass in motion again. Anytime you have mass in motion, that's kinetic energy stored in the molecule. So, kinetic energy stored as translational motion, vibrational motion, and rotational motion.
Then which one is translation?
That's kinetic energy as well.
But how does it know?
Translational motion is just, if I have a ball that's, an object, any object that's moving in three-dimensional space, right? If I take this guy and I throw it, that's translational motion, right? But if I sit there and I do this with it, it's not moving translationally, but there's still energy stored in motion, right? There's kinetic energy stored in the motion of the thing. I just want an excuse to throw something. Get me later on in the semester and I'll start throwing it that way towards the room. Okay. We've all had physics, right?
What's that?
Potential energy. So potential energy is the other way that molecular systems can store energy, and it's arguably the most important. In my opinion, it is the most important because the potential energies stored in molecules are largely a function of the charge distributions. We'll talk about that in a second. And it's those charge distributions that lead to the specific reactivity that different molecules have. And so potential energy is a very big one. We're familiar with gravitational potential energies, right? You take a ball and it's sitting down on the floor. It's got a low potential energy. If you throw it up into the air and put it on the roof, now it's got a high potential energy because it's sitting at a different place in the gravitational field than when it started. It's sitting at a higher energy place in the gravitational field than when it started. Electric potential energies are very similar to gravitational potential energies. In fact, if you remember from physics, your gravitational equation looked something like this. It had the magnitudes of the two masses. This is the general formula for gravity. It's not we're not talking about Earth's gravity, but just the general form of gravity. You got the magnitudes of the two masses. You got this 4 pi r squared term that sits in the denominator. There's probably a permittivity term down there too. And all of that's saying is that there's an attractive force between those two masses. The 4 pi r squared term, I'll tell you this to confuse you, all of that says is that as you move out in a radial distance away from whatever object is emanating the fields, whether it's a gravitational field or an electric field, that the power of the fields fall off as you move away from the object, but they do so in a way that that divides the amount of energy that was present at a little point spot here by the total area of a sphere that has its boundaries at r. And so it's like, if there's something that's a gravitational force, you're going to feel all of it if you're sitting right on top of the mass that's causing that force. But if you move out away from the mass, it's as if the amount of energy that was sitting right at the point is now spread over a sphere that has a radial distance at your position, right? So if you're standing right here, you get that total pull that you feel at point 0 divided by the whole surface area of that sphere, 4 pi epsilon naught, or 4 pi r squared. That's the surface area of the sphere. It's not that important for that class. I just wanted to show you though that the gravitational fields and the electric fields are similar in that they both fall off with the radial distance away from the object And an electric field, just like a gravitational field, is what we're going to call a conservative field, or conservative force field. Any energy that you lose or gain by moving in, from one position to another can be regained when you move back to your original position, right? And so, the same way that we gained energy by taking that ball and throwing it to the top of the roof, we can get that energy back by letting it drop. With a electric field, if we gain energy by separating two charges, we get that energy back when we allow them to approach. So, I'm having a little bit of a time remembering how much I told you about this equation, but let's talk about it for a second. So, two charges, positive and negative charge, right? Did I already do this? Two charges, you get a positive and negative charge. They're attracted to each other, right? So there's a force that is acting to pull them together. If I want to separate them away from each other, what do I have to do in terms of energy? I have to put energy in, right? Because those forces are opposing my motion the same way a gravitational force was opposing my motion to raise the height of the ball. There's a force opposing motion that would cause these guys to separate. And so to get them to separate, you have to put energy in. So put energy into this thing, you can increase the separation. You release energy, you decrease the separation. And so there's a difference in energy between the separated states and the states of close approach, and that is that electromagnetic field potential energy that molecules can store. Bond potentials. This is directly relates to what we were just talking about. An example of potential energy stored in a molecular system is the bond potentials. We'll look at an example of that. So, if you take this system, CH4 and oxygen gas, methane and oxygen, and you allow them to combust. You throw a little flame on it, and some molecular rearrangements occur, some atomic rearrangements occur, the electrons move around, and you get carbon dioxide and water. And there's a bunch of energy released, right? It's, what kind of energy is released? Huh? It's the majority of energy that is manifested as heat in a chemical reaction is energy that was stored in those bonds. And I'm going to explain to you I'm going to try to explain to you where that energy comes from in a loose way. If you look here, essentially this reaction is a reaction that displaces electrons that belong to hydrogen. They were bound to a carbon when we started the reaction off, right? And at the end of the reaction, those hydrogens and all of their electrons have left that carbon that they were originally bound to, and they've joined an oxygen, right? It turns out that the closeness of the approach...
Sorry.
It's okay. Well, I hope it's okay.
I think it's okay.
It happens that the closeness of the approach of the electron, when it is bound to the charge in oxygen, is greater. The closest approach to the magnitude of the forces are greater than the magnitude of the forces, the proximity of the approach, when those same electrons are bound to a carbon. So you can think of this large separation in terms of our analogy here, or of our specific experiment. You can think of this large separation as being H dot bound to carbon dot, right? But when that electron gets pulled away from that carbon and it ends up stuck together to the oxygen, it's essentially been moved down in its electric potential. It's moved to a lower energy state. It's more tightly bound to the oxygen, and you can think of that as the closer approach. So up here, this guy can be thought of as H dot bound to oxygen. The majority of the energy that's released in that, the energy change is a change in the electric potential energy of the electrons in those molecular systems. When you've got electrons bound to carbon, they're at a higher energy, they're more separated from the nucleus than they will be when they're in oxygen. When they bind to oxygen, the oxygen pulls on them with greater strength, it pulls them in tighter, they go to a lower energy position in the electric field than they were at, and you have energy released. Generally as electromagnetic radiation, which manifests itself as heat and other things, can be converted to work, etc. So that's a bond potential. So if we have a system of molecules, like this one here, we'll have a problem with bond potentials incidentally. If you have a system of molecules like this, and you want to store energy in them, say you've got a bunch of carbon dioxide and H2O, you can put energy into that system by converting into CH4 and 2O2. I feel like there's some, is there any confusion out here? We're good? Good, okay, so molecules can store energy as bond potentials. You don't have to have a bond to have potential energy. Well, you do have to have a bond, but you don't have to switch bonding partners in order to store potential energy in molecules. You can also just excite individual electrons. And the excitement of an electron, we're going back to the same exact principle over here. An electron in an excited state is further away from the nucleus than it started. And so to get it there, you had to use force over some distance to push it into that position. And so you have to spend energy to promote an electron up to an excited state. So excited state electrons, usually photoabsorption, will get an electron up to an excited state. You can also run mass at temperatures that are so hot that the collisions between molecules excite electrons. But either way, you can store electromagnetic energy in molecules as excited electrons. The cool stuff is that when they de-excite, they give you awesome things like fluorescence and phosphorescence and all those light signals that we learn to track in the lab when we're watching behavior. Okay? Intermolecular forces. What kind of energy is that?
Electrostatic.
Yeah. Which can also falls under this banner that we've been exploring with charge separation. When you have intermolecular forces, the forces that hold two water molecules together in the liquid, gas, or liquid or solid states, are just the forces between the dipoles on the water molecule. So you got a water molecule that has partial negative charge here, partial positive charge here, and then you've got another one that lines up like this, sticks its partial negative by the partial positive, and throws its partial positive charge down here. Obviously there's some very specific three-dimensional arrangements that water will take, but the point is that the intermolecular forces are caused by this electronic interaction, the interaction between charged regions of the molecule. And so you can store energy in the form of those. Well, if you want to get gas, or sorry, if you want to get water to go from the liquid state to the gas state, what do you got to do? You got to heat it. You got to dump a bunch of energy into it, right? Where does that energy go?
increasing the space between them.
Yeah, it goes into separating these guys from each other. You got to push apart to separate them from their electric attractions. Yeah? And so you can store energy in systems of matter in terms of their interactions. Gas is at a higher energy than a liquid form, right? It all has to do with those intermolecular forces. Water's easy to use because you got hydrogen bonding and you've got dipole-dipole interactions. But all molecules exert intermolecular forces. There's the London dispersion forces, the whole non-polar molecules together that you've learned about in Gen Chem, etc. Okay. Thermodynamics is tricky because I just told you how to think of the energy, the kinetic energy, and the potential energy that's stored in molecules. Thermodynamics only deals with systems that are in equilibrium, and what that means is that a lot of things that we would like to classify as different modes of energy transfer have to be considered very carefully before we assign a label to them. What I'll tell you in the time that we have remaining is that with the right approximations, you can, defining your system correctly, you can break down the energy flow into or out of a system into two principal types of energy flow: heat and work. So, heat and work are just, it's just energy. In fact, the difference between them is very, very small and really only a matter of convention. But they represent mechanisms for changing the energy of a system or surroundings, mechanisms for passing energy between the system and the surroundings. If we say that a system is closed, what's a closed system mean? A closed system means no mass can be exchanged. A closed system, you can't lose any of the particles. So defining a system as closed just basically says you've got the number of particles that you have, that's not going to change. If you have a closed system, you can't lose energy by losing particles. Every particle you lose has some amount of energy, and so if it goes away, that energy goes away. We're going to define a closed system because we want to make sure that the system we're dealing with has no ability to lose its, the molecules that compose it. If that is the case, if you can't lose energy by transfer of mass or matter, then you can break any change in energy that system undergoes. You can break down into a sum of heat and work. Work is these are both mechanisms that energy transfer, that result from collisions. In this case, we're not going to be dealing with electrical work in our system, but the path with which those collisions affect the system are different. Work we think of as energy transferred when you've got directed motion against an external force. We're going to see a lot of work when we look at the expansion of ideal gases. If you've got directed motion of a force across some distance, we think of this as work. Uniform directed motion. If you have random motion where energy is transferred but it doesn't cause any kind of uniform change in the system, if it simply acts to speed up the molecules, their rates of travel in 3 dimensions, the rates of rotation and vibration, etc. If you do that, we call that mode of energy transfer heat. So heat's the stuff that you get when you take a hot iron block and you set it next to a cold iron block, and the vibrating molecules in the hot block bump into the stationary molecules in the cold block and start transferring energy. And pretty soon, the molecules in the cold block are vibrating at the same rate as the molecules in the hot block, and those two blocks have come to the same temperature. Right? So heat can be thought of as the energy transferred as kinetic energy when those collisions pass on their energy to some other molecule. You see that there's electric fields, so obviously you make the connection that there's also such thing as electric work. So if a charge moves uniformly from a region of high potential or low potential, then it's under the influence of a force and it travels a distance. Work is force times distance, and so you can have work that's associated with uniform motion of electrons. We're going to adopt a sign convention. There's something else I wanted to say about work, but I forgot what it was. I have to wait till I remember. Until then, we have a sign convention for a system of interest. If work is done on the system, that is going to cause its energy to change. If the energy of the system increases because of work done on it, we call that a positive change in energy, and so we assign a positive value to the work that was done. If the system loses energy because it does work on the surroundings, we give the work a negative sign. So work will be negative in that case. Work can be conservative or non-conservative. If we do work in conservative fields, then that work ends up being stored as potentials. Non-conservative work, if you were to take an object that was sitting on the ground under the influence of static friction and you were to shove it across the ground, you'd apply a force over some distance, but ultimately the object would still be at rest at the end of the shove, because the energy that you put into it was bled off as frictional forces in the ground. So it's important to be able to distinguish between conservative and non-conservative work. Non-conservative work is the kind of work where once it's done, the energy is kind of bled off as heat. Conservative is where the energy gets stored in the field. So we already talked about heat. Heat is energy transferred in collisions through kind of randomly oriented collisions that don't cause a directed motion of system or surroundings. Sign convention for heat is going to be the same sign convention as you have for work. If the heat is positive, this means that energy was gained as heat. If the system loses heat, then we assign the negative value. It's basically the same exact sign convention as we have for work. If you recast this law and you say, for the closed system, any change in energy has to be associated with heat or work flow across the boundary between system and surroundings. You can break that apart. Heat only really has one form. Work, we said, can be electrical work. It could be electrical work, which is conservative. It could be some non-conservative work. That's what that NC means, non-conservative work. There's other kinds of work that we haven't explored and don't have the time to. Could be expansion work. So there's a bunch of different kinds of mechanisms of work that can result in the transfer of energy. We're going to be dealing largely with ideal gas systems.